Let's talk today about geometric sequences. So, if you could take a look at these three sequences of numbers, try to figure out how the numbers are related and how you would create the next numbers in the sequence. So, take a minute, pause the video, and try to figure out how the numbers are related. Okay, so hopefully you tried this yourself and you noticed that the first sequence each number, the next number in the sequence was multiplied by 3 to get it. So 2 times 3 was 6. 6 times 3 was 18. 18 times 3 was 54. And 54 times 3 was 162. And then it just says it will continue in the same way. The second sequence was a little bit more tricky, so it started at 10 and then the next number was -5. And then the number after that was half of that number, but now it was positive again. So if you notice that each number was half the previous number, then you're multiplying by a half, right? You're dividing by 2, which is the same as multiplying by a half. But really, since it's positive, negative, positive, negative, positive, it's actually multiplying it by negative a half. And the next one, you're multiplying by negative a half. So when you take a negative number, multiply it by negative a half, you get that positive number the next term. So each one is, again, multiplied by negative a half. All right, and then the last sequence, I just threw this one in there to keep you on your toes. Notice that these numbers are actually not multiplied by the same thing each time. You have to add 4 to each one to get to the next number in the sequence. Okay, now this is the type that we already studied. This is called the arithmetic sequence. Remember that that number +4 is called the common difference. Okay, and that would be the D is equal to 4. Okay, so I just wanted you to know that sometimes in these sections you're going to have to decide, is something arithmetic, is something geometric, or is it neither? Is it following a different pattern? So these first two, where you are multiplying by the same thing each time, are called geometric sequences. And that number that you're multiplying each time by the same number is called R, and it's called the common ratio. That's why it's an R, common ratio. And so in this first sequence, the R would be 3, and in the second sequence, the R would be -1/2. Okay, so the explicit formula for a geometric sequence would be a sub n. Remember that a sub n is the nth term in the sequence. So you can plug a number in for n, so the fifth term would be a sub 5. You can also leave it as n, the nth term. And it would be the first term, a sub 1, times r to the n minus 1. Okay, so just like in the arithmetic sequence, we do need to know what the first term is, what that number is, and then we need to know the r, which is the common ratio, and then we'll be able to determine any number in the sequence. The recursive formula, remember recursive means that the next term is based on the previous term. So the recursive formula is a sub 1 is equal to a, some number, okay? And then a sub n is equal to a sub n minus 1, the previous term, times r, okay? And, and also, sorry, n is greater than or equal to 2, just like before. So remember that n is 1, 2, 3, 4, 5, all the positive integers, but it's not going to be 1 because we already know we have to define a sub 1. So notice that really we were using the recursive idea when we were talking about these two examples so far, we were saying, okay, we take the previous term and we multiply by the r, the 3, and we get the next term. And to get the term after that, we take the previous term, multiply by 3 to get the next term. Okay, so the recursive formula, although it looks complicated, it's actually a simple concept that we really probably are already familiar with. Okay, let's take an example. So let's say we're given a few numbers in a sequence. We're going to determine if they are geometric. We're going to write the recursive and explicit formulas, and then we're going to find, I think it was the 50th term. Okay. So we have 1, 3, 9, 27, 81, etc. Okay, so first of all, we have to check, are we doing the same thing each time? And are we multiplying by the same number each time? So the first number, I could be either adding 2 or multiplying by 3. It looks like I'm multiplying by 3 because then 3 times 3 is 9, 9 times 3 is 27, etc. times 3. So it is geometric. And we know that the r is equal to 3. We also know the a sub 1, that's the first term, was given as 1. So for our recursive formula, let's see, we have a sub 1 is equal to 1, and a sub n is equal to a sub n minus 1 times 3. Okay, it's really that simple. Don't plug other numbers in for a sub n or a sub n minus 1, or it won't be a formula that we can use later, right? Explicit formula will be a sub n is equal to a sub 1, so that's 1 times 3 to the n minus 1 power. Now the 1 we could take out and simplify. I don't see the need to. I think it's kind of nice to have it there so you know that the first term is 1. And notice that the explicit formula really tells you that this geometric sequence is an exponential formula, right? This is exponential growth in this case. All right, and then to find the 50th term, so a sub 50. Well, personally, I think we should use the explicit formula because if we use the recursive, then we have to know the 49th term and the 48th, and etc. We'd have to find all the terms. We only have 1, 2, 3, 4. We only have 5 terms. So we'd have to find 45 more terms before we found the 50th term. Very time consuming. That's why there's an explicit formula, right? So that's a sub 50 for the 50th term is 1 times 3 to the 49th power, which would be 3 to the 49th power. Okay, that's a very large number. I did multiply it out for you. Let's see, it was 2.39 times 10 to the 23rd. Okay, a lot of times in this section in the homework even, you will see the numbers left with the powers because the numbers are so large, it does not make any sense to type them out. So instead, you just kind of take them and simplify them and then leave them with the power there. So yes, so this number, of course, would be very large since it's the 50th term. And great.